Hello, everyone. I'm Jean-Luc Margot with UCLA SETI, and today I will talk to you about new estimates of transmitter prevalence. The UCLA SETI search has been going on for about 8 years now, and it is tightly integrated to a university full-length SETI course about SETI, in which students get to use the telescope and reduce data and write code. Then we write papers jointly, and today I will focus on our latest paper published in the Astronomical Journal, and you can find that paper at this link, bit.ly/AJ23. We use the Green Bank telescope in L-band, and we search for narrowband radio signals. We are sensitive to an Arecibo telescope out to about 125 parsecs, and we're sensitive to something like a 70 Arecibo telescope out to a kiloparsec. And finally, we could detect a civilization all the way to the center of the galaxy, provided it had a transmitter power equivalent to about 4,000 Arecibos. Here's a summary of what we've accomplished to date. We've searched multiple fields and recorded signals from about 55,000 stars in the beam of our observations. And we've detected 82 million narrowband signals. Here's an example of a dynamic spectrum with time increasing down and frequency increasing to the right. And one important characteristic of our search is that we maintain the full resolution, both time and frequency resolution of the data. So our spectra are about 3 Hertz wide, and we maintain the full time resolution. So we have one spectrum every 0.3 seconds approximately. And this is in contrast to the current process in the breakthrough listen pipeline, where there's a incoherent time average by a factor of about 51 to help reduce the amount of data. There are consequences to this incoherent averaging, especially in terms of sensitivity and overall pipeline efficiency, which we'll talk about today. This is the range of drift rates that we cover, approximately plus or minus 9 Hertz per second. And we're fairly content with that range. It allows us to detect line of sight accelerations from most of the confirmed exoplanets. This is the orbital component of the line of sight acceleration. We can detect about 73% of confirmed exoplanets. And if we require that the semi-major axis is larger than 0.1 AU, then we can detect 100% of these accelerations. And in terms of accelerations due to spins, we can detect 100% of Earth-sized planets, provided that they spin less than the breakup rate, and we can detect 100% of Jupiter-sized exoplanets, provided that they spin less than about 12 hours. Here's a summary of the distribution of our detections with a log scale. Again, this is L-band, and we've detected in this 4-year survey of a sample of test targets, we've detected about 41 million signals. 99.4% of those are automatically rejected as radio frequency interference. That leaves about 200,000 candidates, of which about 500 are in regions outside of very dense RFI, and we visually inspect every single one of these signals. We've had lots of interesting signals, but none that that have required reobservations to date. In other words, we've been able to ascribe every single one of these signals to anthropogenic interferers. One of the main results of our recent paper is a signal injection and recovery analysis, where we've quantified the performance of a pipeline by injecting 10,000 artificial signals in the data. And we chose a uniform distribution in frequency, with the exception of a frequency range corresponding to a notch filter at the GBT. And we've chosen a uniform distribution in drift rates. And we can inject these signals. Here are some examples, either in the power spectra or in the raw voltage data. And here are the results of that analysis. The injected signals here are shown in brown, and the recovered signals are shown in yellow. We find that we can recover overall about 94% of the signals that are injected. And we find that the performance depends strongly on the RFI environment. In other words, outside of regions of dense RFI, our performance is actually closer to 99% recovery. Overall, we recovered 9,400 signals out of the 10,000. The distribution in signal to noise and drift rate is exactly as expected. We also injected the exact same signals in the data and conducted a breakthrough listen-like processing of these data. So we did the time average by a factor of 51, and then we ran the Turbo SETI detection software as opposed to our own. And these, this table shows the number of hits prior to injection, the number of hits after injection of the artificial signals, the candidate matches, and the actual matches where we actually carefully match a tolerance in both frequency and drift rate, and the overall pipeline efficiency. And what you can see is that for a breakthrough listen process with a 51 time incoherent averaging, the sensitivity at high drift rates decreases dramatically, and you're not able to recover these signals. And this is consistent with our predictions based on the dechirping efficiency considerations that we had described in our 2021 paper. So again, if you look at the signal to noise ratio as a function of drift rates, if you do incoherent averaging, you see a sharp drop as the drift rate increases, and that explains the difference in performance. Now, this overall pipeline efficiency has really important implications when it comes to computing upper limits on the number of transmitters out there, or when it comes to computing estimates of the surge volume that has been searched to date. So one popular metric for the surge volume is the Drake figure of merit. And it's really good in that it captures the bandwidth, the solid angle, and the flux of a search. However, it assumes 100% pipeline efficiency, and that is not a good assumption. And it also ignores the drift rate coverage. We are suggesting that we should include both of these components in an improved figure of merit, for instance, by including the drift rate coverage and the overall pipeline efficiency as shown here. When we do that, and when we compute the search volume of the UCLA SETI program, we find that it falls somewhere in between the survey of 692 stars, primary stars, I believe, of Enrique et al., and the survey of 1,327 primary stars of Price et al. With the overall pipeline efficiency, we can come up with rigorous estimates of transmitter prevalence. And we describe a formalism in our paper where we consider a SETI experiment as a set of Bernoulli trials with a probability of success P. And that probability of success depends on three factors: the fraction of stars with transmitters, the overall pipeline efficiency, and the transmitter duty cycle. Now, if you conduct n observations or trials and detect 0 extraterrestrial narrowband signals, you can write with a certain confidence level an expression for that probability of occurrence. And you can solve that to define an upper limit on the transmitter prevalence, which is this expression right here. It simplifies very nicely if your pipeline efficiency is close to 100% and the duty cycle is 100%, and you assume a 95% confidence level, then it becomes this expression 3 over n, where n is the number of trials, and this is known as the rule of 3. We've computed these 95% confidence level limits for our survey. We observed 10,000 stars within about 6.1 kiloparsec. and we infer an upper limit of 3 times 10 to the minus 4 limit on the number of transmitters. Within 1 kiloparsec, the limit is about 2 times 10 to the minus 3. And on this diagram showing the maximum fraction of stars with detectable transmitters as a function of duty cycle, we again see that our search is within a factor of a few of breakthrough listen searches. In this case, we've had to revise the published estimates because previous authors had assumed that this pipeline efficiency was either 100% or 50%, which is not the case. So this graph takes into account these correction factors. Finally, I'd like to mention the AI detections of Peter Ma et al. These were detections that had escaped the breakthrough listen pipeline and that Peter and others identified with AI techniques. We reprocessed their data through the UCLA SETI pipeline, and what we found is that we can detect these signals natively without AI assistance. And in addition, our pipeline tags these signals as radio frequency interference. I want to acknowledge our funders. It's primarily private funding. We also have a 3-year grant from NASA. And I will leave my conclusions up here, and hopefully we'll be able to answer some questions. Thank you.